Alright, so these are the three exceptions that you know so far. Hydrogen only needs how many electrons? Two. What about beryllium? And? Good. Like robots. Okay, there are two more exceptions. Really, one more exception and then polyatomics, okay? So the other exception, which I mentioned Wednesday, but we didn't have time to get to it, is what we call the expanded octet. What do you think that means, expanded octet? It's going to have less than 8 or more than 8? More than 8. That central atom is going to have more than 8 electrons, okay? And there's ways to recognize these. These are only elements that are in the D level or below. So it starts with period 4, because remember that's where the D's start, right? 3D is in period 4. So anything from period 4 or below can be expanded octet. There's a couple of ways to recognize these, okay? So I'm going to go over them with you. If you do your formula, if you do your needed available shared formula and the number of bonds that you get do not make sense with your formula, then that is the big kicker, red flag. This is probably expanded octet. Check your element. The central atom, if it's in period 4 or below, then it's expanded octet. So at that point, all you do is do your skeleton model, put your octet around your outside atoms. Any extra electrons that might be needed will go on the central atom. It's not hard. Let's work one and you'll understand what I'm talking about. All right, let's look at this one. Okay, so this is a covalent bond, non-metal. Which element's going to be in the center of your skeletal structure? Phosphorus. And then we should have 5 F's, right? One. Now you notice we can't put them like we have been doing in the complete T because we got 5. So you just place them around here. Okay, that's 5. You're still going to set up needed, available, and shared. Okay, so we have said every element needs 8 except for these 3. Is phosphorus one of these 3? Nope. So it needs 8. What about fluorine? It needs 8, right? But we have 5 of them. So we add these up with order of operation and we get 48. Oh, I just erased the whole formula. All right. How do we get available? What did we do to get available? Look on the periodic table. Get the ones that are actually available to use for bonding. So for phosphorus, how many do we have? 5, and there's only one of them. For fluorine, it's in group 17. 7. But we have 5 of them. So what does that end up being? 35 plus 5 is 40. Then we subtract, and then we divide by 2, and that gives us 4 bonds. Now, I want you to look at your skeletal structure. Does that make sense? We've got 5 fluorines. We're only getting 4 bonds. Can you do that? That should be a red flag going off that, hey, something's wrong. I need to look. Okay, is phosphorus or phosphorus is in period 3. It is not a D block. Anyway, it is in period 3. It should be 3D, so this one's not a great example, but this one is expanded octet. Anytime you have a lot of atoms around the outside, you're pretty much going to have an expanded octet. Okay? This one's not working out as far as looking at the periodic table, so I don't want to tell you to look up there. But if this doesn't make sense, and you've got several atoms around the outside, then this is what you do. You connect all of them to the central atom. You fill the octet on all of the outside atoms. count up all of your electrons and see if it equals your available. If it does not, if you're short, then the extra lone pairs go on the central atom in a spot that you don't already have an atom attached to it. Okay, so easy way to count this up, we know that each of these fluorines has 8, right? And there's 5 of them. So 5 times 8 is 40. That matches. So there's no need to add any lone pairs on the phosphorus. If we were short 2, let's say we ended up with 38, then we could put them here. We could technically put them there. You understand what I'm saying? You just have to add in the lone pairs. This is where we get the expanded octet. It's already expanded, right? Because look at phosphorus. 2, 4, 6, 8, 10. It already has 10 electrons attached to it. That's why I'm saying if you've got multiple atoms around one central atom, you pretty much know it's expanded. No, not an expanded octet. That's what I'm saying. That's an exception. Don't you love them? They're great. All right, let's try another one. Oh, this one's a fun one. Let's look at it.
I sent it sarcastic.
Okay. What would your skeletal structure look like? Eye, and eye, right? You got 3 eyes. So maybe just something like that. Now, what do you notice is different about this structure, about this formula? It's got a negative charge. You got it, which means it has more electrons than it does protons. So if I were you, I would go ahead and put this in brackets, and I would go ahead and put your structure in brackets. And go ahead and put the charge in there. All right, anytime you have this, like a polyatomic, okay, all of your polyatomics are going to have that charge out there. You're going to have to either add them in or take them out of your available when you're doing the count. Okay, now listen to me. If it's negative, you add them in. If it's positive, you take them out. So this is -1, so we're going to add 1 electron. Think about it. If it's more negative, that means it has more electrons. So you would add it in. If it's more positive, that means there's less electrons. You're going to take them out. All right. So let's look right here. For needed, how many does iodine need? 8. There's 3 of those, right? So what do we get? What about available? Available is 7. So there's 7, but how many do we have? 3. Break time. Chick-fil-A biscuit time.
Well, now, if you want something that's snack drinks, Chick-fil-A.
Appreciate it, babe. I'm dying. Anybody else? Good? Thank y'all. All right, guys. So back to this. We've got 3 of these atoms. So 7 times 3 is 21. Now, there should be red flags going off right now because what did I tell you?
Never have it.
You're never going to have an odd number right here. Okay, we're getting 21. We have not added or subtracted that extra charge. If we add that, because it's negative, so we add 1 and we get 22. We subtract, we get We subtract, we get 2. Now, if we divide by 2, we get 1 bond. Does that make sense with this structure? No, it doesn't. Look and notice where I is at. It definitely is down past period 4, right? So this is expanded octet. So we said, we draw our bond lines. We fill the octet on the outside atoms. So that's these 2, right? Then what do? Yeah, we count up our electrons and we make sure that we get 22. 2, 4, 6, 8, 10, 12, 14, 16. Okay, I'm getting 16. How many are you guys getting? So how many extra do we need on that middle I? So 3 sets, right? So how about 1, 2, 3, 4, 5, 6?
So if it's in period 4, it's going to be expected.
Yes. For the, well, not always, but for the most part. I'm going to try not to trick you. If it's expanded, I want you to, like this one would be a tricky one. This one would be tricky. I would probably give you one with like 5 atoms around the outside. So we just hit, this one hit expanded octet and like the polyatomic with the extra charge on the outside. You have to add in or take out that charge. Let's look at one. Do you guys want to do one with a polyatomic? Okay. What polyatomic is that? That's one of the ones on your list. Carbonate. Good. You've been looking at yours. Carbonate. This is carbonate. So I would go ahead and put this in brackets. You know it's a polyatomic because it has a charge. Okay? And then, which one of these is going to be our central atom?
Carbon.
Carbon.
Markers not added.
So I'm just going to put an O there, an O there, and an O there. I don't know how you guys want to do it. And I'm going to put my brackets around it with my charge. It's really important that when you're drawing the structure that you put the brackets around it with the charge. That's just how you draw the structures for polyatomics because that charge goes to everything. Remember that video? There's a little bit of this charge on every atom. All right, needed, available, shared. All right. How many does carbon need? 8. How many does oxygen need? 8, but there's 3 of them. 24. 32. It does end up being 32. All right. Form available. I'm going to go ahead and start it because I know I've got to do something there. All right, hang on. How many does carbon have available? 4. There's only 1 of them. How many does oxygen have available? 6, but there's 3 of them. So that's 18, 19, 20, 21, 22. Now that's even, but we still have to do what? Do we add 2 or subtract 2? Add. So we add them in and we get
8. I said 8.
What is that? 8? It was, nope, I'm subtracting.
Oh, okay.
I was subtracting.
I was like,
Leaving out the steps of my subtraction. You get 8. We divide by 2, we get 4. Now, here's my question. Would this be considered an expanded octet?
No,
No, it's not, because carbon and oxygen are further up in the periodic table, right? So what are we gonna do to get 4 bonds in here?
Put two.
One is going to have a double bond. Beautiful. At this point, I don't care which one you put it between. So I'm gonna put it here, 1, 2, 3, 4. You might have put it here, you might have put it there. Alright. What do we do next? We gotta check for octet on all these suckers. So for this oxygen, 2, 4, 6, 8. For this carbon, 2, 4, 6, 8. So it's good. For this one, 2, 4, 6, 8. And for this one, 2. These are tricky ones. Okay, these are real tricky. Yeah, check us out, Ahmad. Did we match up?
We do.
Awesome. So if you add all of the electrons up, we get 24.
Unless it's expanding, and expanding with the lines that should inflow to.
You can have more bonds because you're going to have double and triple bonds. You shouldn't have less bonds than what there are atoms to bond them to. Does that make sense? All right. So this brings me up to a new vocabulary word. Okay, this is called resonance. And what that means is that this double bond can be here, it can be here, or it can be here. That's what we call a resonance structure. So that thing can change, and it's kind of like a fan. If it were going, the best example I have is like if a fan were going, this thing could be on either one of the atoms. Does that make sense? But it's still the same thing. It just can be drawn differently. Resonance structure. You had something like this. It could also be drawn. What am I doing? Yes, in the middle. It could be drawn like this, or it could be drawn like this, with the lone pairs added. So that would be a resonance
So
structure.
it's just the same thing, different.
Same thing. The bonds are in different places.
So that double bond would be a resonance.
Resonance. This one could be resonance. If I change that double bond, put it here. If I put that double bond there. All right. How are you guys feeling? So this is my plan. On Monday, I'm going to give you. It's a homework sheet, but it's basically going to be a review. It's going to cover electronegativity. It's going to cover characteristics of bonds, and it's going to cover electron transfer diagrams and Lewis structures. If you can do this worksheet on Monday, you should be ready for a test on this stuff. Okay? So it's kind of like your review for a test. Now, we're not having a test on this next week because we're having a polyatomic test. But it's coming, is what I'm saying. I'm not going to do the ingenuity. I'm just going to give you a test in here. Old school, like I used to do last year. Well,
There's garbage.
it's wanting you to do a lot more stuff, and I want to go in a little bit different order than ingenuity, so it's kind of going to mess us up.
Ingenuity is trash.
I learned from one.
The only good thing about ingenuity are electro.
All right. So we did not do the flashcards, so we'll run through them right quick, and we can cut this off.